Now we return to the situation with the pulley and the rope with 100 gram per meter mass density. 6 kilograms on one side, 5 kilograms on the other. This mass 1 meter below the pulley, this mass 19 meters below the pulley. What we want to find, and we reviewed that, we got a net force from this situation. It's equal to the, with the counterclockwise direction being positive, equal to negative 60 newtons, the negative 60 newton weight of the 6 kilogram mass, which is pulling the system in the negative direction, the clockwise direction. 50 newton pulling it around the counterclockwise direction. Minus 1 newton per meter times x, where now x stands for your position. Okay, here's your x-axis, and at some point with maybe coordinate x here. So when you're at this height, this is going to be the net force. Now the reason for that, 1 newton per meter times x, x being the distance from here to here. You have x meters of rope at 100 grams per meter. The weight of 100 gram mass is 1 newton, so you have 1 newton of force for every meter of rope over this side pulling in this direction, which is the counterclockwise, so you have negative 1 newton for every meter times x. On this side, you have 20 meters minus x, and it's doing the same thing at 1 newton per meter. And that gives you a net force of, this gives you minus 10 newtons. The 20 newtons times 1 newton per meter gives you 20 newtons here. And then you have minus 1 newton per meter times x here, and again minus x times 1 newton per meter here, so you have negative 1 newton per meter times 2x over here. So now we have negative 10 newtons plus 20 newtons minus 1 newton per meter times 2x, and that comes out to 10 newtons minus 1 newton per meter times 2x, and that's our net force as a function of x. You'll recall also, and if you don't, you should review it, that we derived a differential equation in time, differential equation with a variable of time, that we don't know how to solve, that will tell us the motion of this object as a function of time, given its initial velocity. Okay, and that's something that is not that difficult to solve around the third week of January in a differential equations course that runs for the winter. We get that. Still, we don't have the technique now to do that, but we do have the mathematical techniques to analyze this. We won't get the equation of motion, but we will be able to find the velocity of this object at any point using the work kinetic energy theorem that we derived in the preceding video. Okay, so we can say now that the change in the 1/2 mv squared using that result between x equals 1 meter and x equals 19 meters, between here and the floor, just for one example of what we can do, we can find that change by finding F net delta x, because the change in 1/2 mv squared is the change in F net delta x. However, we've got a problem. F net delta x, F net is not constant. If F net was constant, then we'd just be able to do this in just one step. But F net is a variable force. So in that sense, this is not a great question. There's not just one answer to what is F net, or what F net. We don't know. If there was just one answer to what is F net, we just multiply that by the 18 meter displacement, and we know the change in this quantity. However, F net is a variable quantity. So, well, I'd ask people, okay, what from calculus do you do when you have you want to do something like this? I didn't form too many leading questions because I was hoping somebody would come up with it. Somebody did. Said, well, would you do an integral? Yes, you would. There are many reasons to justify using an integral, but let's just use the intuitive idea right now that you would use an integral, because we don't want to get into the local to global development, getting a Riemann sum and everything, and we need to be able to do that. We'll address that. But right now, we're just going to say, okay, let's just integrate this function with respect to x. Okay, well, two ways to look at this. The integral of the function with respect to x makes sense because the function is a function of x. So we can certainly integrate this with respect to x. We can find an antiderivative very easily. It's a simple linear function. We're going to get a quadratic antiderivative. And then we're going to be able to use the two limits on the integral to find this. Also, we note that the integral of f net with respect to x over some interval of x, from x equals 1 meter to 19 meters in this case, is equal to the average value of f net times delta x, which is equal then to the average value of f net times 18 meters. We could actually shortcut the integration process. I didn't do that, but we could shortcut the integration process here because f net is a linear function of x. So we could just take the initial value of f net, which occurs when x equals 1 meter, and the value then being 8 newtons, and the value of f net when x equals 19 meters. Now, at 19 meters, we're going to have negative 38 newtons from this term, and 10 newtons here is negative 28 newtons. So we've got 8 newtons averaged with negative 28 newtons. Well, it gives us an average force of what? If you average 8 with negative 28, 8 and negative 28 adds up to 20. Divide that by 2, you get 10. So you should get, the difference between these is 18 meters. 18 meters times 10 newtons, 180 newton meters. Now somehow I got 182 here. And we did this kind of quickly at the end of class, and I did something in my head, and I screwed up and got 2 meters where I shouldn't have gotten them. Should be 180 newton meters, but we'll look at it a little more closely here. Okay, so we integrate this, and of course we have to integrate the whole function. So I need parentheses here and here. And antiderivative of 10 newtons is 10 newtons times x. The antiderivative of x is 1/2 x squared, so the antiderivative of 2x is just x squared. So I get 10 newtons times x minus 1 newton per meter times x squared. Okay. Now, square 19 meters, you get 361 meters squared. So that gives you minus 361. Yeah, it's negative. Okay. Minus 361 newtons per meter times square meters, which comes out to negative 361 newton meters. And then plug in 19 meters for this, you get 190 newton meters, positive. 190 minus 361 is negative 181 joules. Then you have what you get at the 1 meter. And I'm still getting a negative. What do we get here? We get, actually it's probably 191. Okay, we get minus the 10 newtons times x, which is just 10 newton meters. And we get a minus 1 newton per meter, giving us a negative 9. I'm still getting 182. I'm not going to write it out. I've something gone haywire in my brain that's still there from a couple of days ago when we did this in class. Should be 180 because of the linearity of this. Either I messed up with the linearity here, and I don't think I did, or I'm still off by 1. I think I get it's not making sense. I can't get a negative 11. Numbers aren't hanging together. I'll probably do a little addendum. I don't want to work this out on the camera while I'm on camera. Okay, in any case, we get something like negative 180 joules. And this tells us that we should get negative 180 joules. This tells us that the change in our 1/2 mv squared is negative 182 Newton meters. Now I'm using joules here. I'm kind of skipping to that. Let's stick with Newton meters. I made the comment that this is joules, but let's pretend we haven't heard that before, because in this class we haven't. Negative 182 Newton meters. Our change in 1/2 mv squared has to be negative 182 Newton meters. Now we ask, if we just release this thing, what happens? How long does it take it to get down here? Well, I can tell you without even thinking about the fact that the net force takes it in this direction and it doesn't get down here, that it isn't going to get down here. Because if I start from 0, 1/2 mv squared is 0. Okay? The change in 1/2 mv squared is negative 180 Newton meters. Now if I start at 0 and change to negative 180, that means that my 1/2 mv squared down here would have to be negative 180 Newton meters. However, 1/2 mv squared can't be negative 180 meters. Why not? Because m is a scalar quantity and it's positive. V is squared. It can't be negative. So 1/2 mv squared itself can't be negative. Now the change in 1/2 mv squared can certainly be negative, but 1/2 mv squared can't be negative, so we know that it doesn't go from here to here. Okay. Now if I give it an initial velocity, give it a good thump here, get it moving fast enough, it can get down here. It can overcome the effect of this force, because as we saw earlier, there is a point not too far along where the well, let's just think about it. If these two were at the same position, you'd have the same amount of rope on this side as this side, but you'd have more mass. The 6 kilograms is more massive than the 5 kilograms. So by the time it got to the point where the two weights were passing each other, it would accelerate down this way, and it would continue on. So there's some point up here, kind of a point of no return. If I give it enough initial velocity to get to this point, then the two forces are going to balance, and then in the next instant, this mass is going to have moved on a little further, and you're going to have more rope here than you got over here, so you have a net force in this direction, or more rope than you did, and it's going to continue on. Okay. So you ask yourself, what kind of speed do I have to give it to start out? Well, I have to give it enough speed that its change in kinetic energy will be negative 180 Newton meters. Okay, that the F delta X is going to be negative 180 Newton meters. If I don't give it that much speed, it doesn't have enough 1/2 mv squared to have that much change. It's got to have at least 182 Newton meters of kinetic energy here, or of 1/2 mv squared here, in order to get here. And you can then, knowing the mass, and that would be the total mass of the system, because it's the total mass of the whole system that's being accelerated, you could put in total mass of the system and set 1/2 mv naught squared equal to 180 Newton meters, and find out just how fast this thing would have to be going initially. Now this bypasses all the kinematic equations. It bypasses any time dependence. It doesn't tell you anything about time dependence, but it does tell you whether we can get from here to here if I give this thing a certain initial velocity.